2, 1. Hello and welcome to Digital Futures. Today we have yet another session on workshop outcomes from our very intense session during summer. Today we have 7 of the workshop instructors presenting their outcomes from robotic fabrication. We are joined by instructors who are from different language groups, but everyone, today's session will be presented in English for the larger audience to be receiving it. The session is going to start with robotic mark making with Sara, Codarin, and Karl Daubmann, who are joining us from LTU, followed by programming for digital fabrication from the Japanese workshop, and then followed by 3 other workshops which were held from the Arabic language channel and were held both in English and Arabic. And the last 2 workshops are from the Spanish group. So we're happy that this discussion is happening, and it's going to bring out some really interesting observations and questions for us towards the end of the session. So stay tuned for the panel discussion. Without further delay, let me call upon the first presenter, Sara, Codarin, and Professor Karl. Just a brief introduction to Professor Karl. He's an architect at the forefront of digital design. He is the Dean of College of Architecture and Design at Lawrence Technical University. His teaching areas include design, digital design, robotic fabrication, construction, leadership, and multidisciplinary design. His design practice, DAUB, focuses on expanding the relationship between technology, design, and practice. Professor Karl is a fellow of American Academy in Rome. Between 2010 and 2014, he was the Vice President of Design and Creative Director for Blue Homes, where he led a multidisciplinary team that developed prefab housing. Professor Karl, we're happy to have you. Sara, who is joining us today, is also going to be moderating the panel discussion with me. She is a techno-optimist and she loves robots. She completed her PhD at the University of Ferrara in Italy, where her doctoral research investigated robotic manufacturing for the conservation of cultural heritage. She spent an academic year as a visiting scholar in College of Architecture and Design at LTU to develop an experimental application of her research. Her experiments simulated on-site robotic fabrication processes to produce custom units for recovery of damaged buildings. Sara and Professor Karl, the screen is all yours.
Thank you so much, Evelyn, for the introduction. I will share my screen. Hopefully you can see everything all right.
Yeah, looks good.
Perfect. So thanks a lot. Thanks for this opportunity for presenting the workshop that we held at the College of Architecture and Design, our workshop called Robotic Mark Making. That we had this summer with a cohort of international students. So my name is Sara Codarin. I'm an assistant professor at the College of Architecture and Design. And
Karl Daubmann, the professor and the dean in the college as well. Me?
Mm-hmm. Please.
I think we wanted to maybe just talk about some of the motivations for what we were trying to do while we were using the robot to produce drawings with the students. We also talked to them about some broader issues, like the role of procedure within what we do as architects, and also really the mediating condition that we find ourselves in, right? That we design something, but as these things scale up, we often rely on others to execute that work. And so we kind of like going far back. And I think a lot of people talk about these types of ideas and go back. I like Durer's alphabet as one example where I actually talk about it with students as a kind of script, right? And then that text description that's on the right is the text description on how to construct the letter E. And we see that whether it's through traditional drawings, construction documents that we've seen in the past, or a direct contact with the robot as a way to produce something. And so we try and set up this as an idea with the students. And then we continue to go into these things, right? If we think about that mediating condition and having to communicate, we also think about the role of labor. And whether that be a kind of human condition or an automated condition, there is the need to think about what maybe those constraints are, how these things operate. And so we loved kind of making this connection between the Gilbreth motion studies, which have a long history in kind of industrial realms and efficiency, but we also love them for their kind of beauty and the way that they capture the time aspects of movement. And I think that's part of what we pulled from when we started to think about robotic mark making and that role of the line, and that each line is a kind of passage of time, and that those things build up a kind of density. And we see that in these kind of long exposure photographs. And so we're trying to play off both of those things.
And as we mentioned, we had the possibility to interact with a cohort of international attendees for the workshop. And so we really wanted to frame the workshop in the context of Detroit, where LTU is located in Metro Detroit, which is an area in the States with the highest concentration of robots. And they are a driving force in the Midwest, and there is a close relationship between the industry and higher education. So we wanted to leverage and to talk about the legacy of manufacturing in the area. I wanted to use this as motivation to talk about the culture of manufacturing as part of the local heritage.
And maybe, I mean, I like Sarah's introduction that she loves robots, but I think if you ask her where she wants to be, she came to Detroit where most of the robots are. And then our robots came through Ballard International, which is a group that buys robots that have been decommissioned and then resells them. And so that map looks quite similar in terms of aggregating robots and then redistributing them to places like places of higher education, smaller manufacturing facilities. And so we're seeing that the change, or maybe the democratization of robotics coming through aspects like that.
And we wanted to focus on line work primarily as a formal outcome of our workshop. And as Karl mentioned, we thought about lines in terms of procedures, in terms of time, in terms of algorithms. But also we wanted to frame a little bit of like the theoretical aspect of that, talking about this formal element as a metaphor for other things, as a metaphor for society, as a metaphor for communication. So really trying to expand the conversation in as many directions as possible. And we share with the students some precedents that we thought were relevant in terms of pioneers of the digital art that explored formally lines as a way to understand the way we conceptualize them, and how they are like a basic component of the human thought. And we wanted to look at some examples like Solowit, for instance, in terms of like procedural studies, but also a precedent that we consider important to mention is the work of Vera Molnar that does these beautiful methodical explorations that we use as a reference as well in terms of like the aesthetic language that we were hoping to achieve through robotic fabrication, and trying to merge in a way, or like to put into communication, automation, and craft.
And then it was also important for us to maybe project what a line could be from an architectural sense. So examples that we kind of, either some examples that we've done ourselves or things that we've looked at. So Louis Kahn's traffic studies, where those lines not unlike the long exposure photographs that we saw from the Gilbreths, here talking about traffic and kind of diagramming those things. The next example, a series of lines that were inscribed using a CNC, which start to evoke a kind of space, but also a materiality. And the work of LTL in one of their earlier projects where the lines start to become, or the conduit, we understand as a kind of procedural line and the way that that was produced. And so the way that we use lines in space, the way that we use lines to produce form and density, were things that we imagine maybe the robot being able to be deployed to think about both representation and the eventual execution of those things.
And so we were able to conduct these conversations and these discussions with a group of people, amazing people from different locations, different backgrounds. So it was great to be able really to have these discussions, but like being able also to teach remotely these processes and to and also like for them to experience some of those things firsthand, though remotely. And just in terms of what we have done in a week, basically we structured the workflow in three sessions, and trying to pursue in a way different formal objectives, starting from line work, and then we wanted to take as inspiration some like physical rules, starting from the magnetic fields, but also the flow lines in terms of understanding the vectors of possible flow that goes through a topography. So those were like the three main topics of the workshop. And we were trying to obtain results to make drawings that were unique and in a way not repeatable. So we decided to deploy this approach that it's different from plotting. So of drawing in the three-dimensional space, and use a soft brush installed to the robot to really be able to play to line thicknesses based on the position in space of the two center point, to be more technical about that. And we started doing some studies. And also part of the process was we took notes along the way through a sketchbook to see how the results could change based on the different settings, technical settings that had to be mediated through situational conditions like the life of the soft brush, but also the humidity in the space, and also like it was nice to see the technology dissolving in a way in the physical results. So some documentation of the process, but also to visualize a little bit better part of the process. We called it 2.5D drawing, actually. So like really creating three-dimensional line work and then compressing it in a few millimeters in a Z direction. And so really creating something that it's hard to simulate in the digital space, but it was a nice surprise to see again, like the drawings being less digital in a way. So that was a little bit the intention, and just some examples. And from the students, that's collection of images of the drawings that we documented along the way, and we were able to discuss with the students. Also part of the—
If you go back one, sorry. It's also really exciting when you have an idea, like we prototyped everything so that the workshop would go smoothly, but then moments when the students can manipulate the script or change something and then produce something very unexpected for us. So there was a really nice, it wasn't just a kind of one-way relationship with the students. There was some dialogue that was back and forth, and it changed the way that we thought about some of these things too, which was exciting.
And it was nice also looking at the details and starting really to get away from the digital control of some of those things of this design, and starting to lose the directionality of some of these lines and really going and seeing what happens when the ink does the job of dissolving the digital work. Basically, at the end, we wanted to celebrate with the work with an exhibition at the College of Architecture and Design, and we had the original drawings, and we took all the documentation for the students. We had webcams around robots to show them the process, and at the end, they had the satisfaction to see the work exhibited in our institution. But also thanks to Digital Future for like this amazing opportunity of seeing our line work casting shadows in the metaverse. So we thought it was a fantastic experience, and we want to push this forward, and we are very excited to promote the next steps. This workshop will be part of Acadia 2022 at Penn University, so we'll be again the host, and yeah.
Yeah, thanks.
Thanks a lot for your attention, guys.
Yeah. Thank you so much, Professor Karl and Sara. It was really a delight to just see the work, and it's amazing. I can't wait for the panel discussion to begin to ask you questions. Moving forward, let me just give a brief introduction to our next presenter, Tsuruta. Sorry for the pronunciation in case I went wrong. Ko is an architectural designer focused on material-aware fabrication with the concept of form follows availability. He has taught as a tutor at Gramazio Kohler in ETH Zurich and as a teaching assistant at Tokyo University of the Arts. He is co-founder of Codarin, a design research studio focused on practice with machine intelligence, with AI, robotics, and 3D scanning. His work has been awarded at various competitions, including 2019 SD Review and 2019 Committee Colbert Award. His master's thesis at DFAB in 2021 in collaboration with Simon Griffon was accepted at 2021 IROS workshop, Robotic Fabrication, Sensing in Additive Construction. Ko, we are happy to have you here. Ko was also part of the first Japanese hybridity session as well. So, Ko, good to see you again.
Thank you for introduction and having me at the future talk on robotic fabrication. It's such an honor to get an opportunity to share my practice around robotic fabrication. So let me start sharing my screen in a slideshow. I hope everything is clear to you.
Yeah, looks good.
Great. So I'd like to start. Yes, thank you for having me again. And I'd like to share my practice using the core concept of my workshop, Digital Futures, just because it was quite a fundamental workshop, so there was no basically visual outcome. So I'd like to share other practice based on the same frameworks. So I finished MS ETH last year and worked at Codarin Research as a tutor, and I'm currently working on a master thesis at Tokyo University of the Arts. So my university, as its name shows, is a quite traditional art university, and its curriculum is quite unique. And this is because it's wide range of scope in the course of architecture department. From the first year, some traditional classes like planning or sculpting are given, and at the same time, we are taking the course for digital literacy like modeling in Rhino or Grasshoppers. So by encoding and decoding materials through our body and computer, we learn how to face with the real world as an architect. So one of the advantages of this education is an adaptability of this knowledge. And I'm also part of this process, and there are many research and works by using many different materials, from traditional materials to relatively new materials. So in every project, I, as a researcher, try to find a space for intervention in the material property or material digitality. So the idea of this material digitality is the digital aspect of the material, especially from a machine perspective. In other words, how is the digital understand the material? So in order to share this idea, I'd like to introduce my recent practices. So intuitive robotic plastering is the first project. So I'd like to show videos first.
Welcome to the construction site. Please mark the points on the ground. You can start drawing. Time to select your tween type. Use trackpad to reach higher. So this project was led on a conversation between the human and machines through plasters as a main material. So in the beginning of this research, it was quite difficult to predict material behavior from our body motion. But however, the more lines we draw, the more precise our intuition became. But this is a good example of the process of learning material digitality through our body. So after developing a mutual understanding between the materials and the tools, the materials was parameterized and we obtained reproducibility of the wide range of textures. So even in the process of construction, we kept sort of train our intuition on site, like on a traditional carpenters. So the next project is in the deep landscapes, a design tool for robotic sand shaping with GAN-based height map predictions. So the digital fabrication has a potential for more sustainable architecture construction by allowing the use of abundantly available natural materials. However, accessibility to these materials is limited because of its unpredictability. Therefore, our thesis is aimed to explore an alternative approach to design a fabrication process with the natural materials by introducing machine learning. So in the context of fabrication, there are many approaches also in ATH, but we were wondering how machine learning approach can assist in this design landscape with natural granular materials. So several strategies exist, like a numerical approach,
Thank you, Ko. Maybe, yeah, we'll wait for the panel discussion to ask you more questions. I'm hoping there are more from the YouTube audience as well for you. Just moving forward, I'll just hand over the screen to Reem, who's going to introduce the next three workshops. Reem is the language coordinator from Arabic channel. So Reem, yes, please go ahead.
Hi everyone. So I'm gonna start by introducing the next speakers, Dr. Sherif Abdelmohsen and Dr. Geneidy. So Dr. Sherif Abdelmohsen is an associate chair of the Department of Architecture at the American University in Cairo. He's also an associate professor of digital media, design computing, and the director of Robotic Fabrication Lab at the Architecture Department at AUC. He's the co-founder of UDAR Engineering Consultancy, and he's also the president of the Arab Society for Computation Architecture, Art and Design, known as ASCAD. He received his PhD degree in architecture from Georgia Tech, and he has over 70 articles in parametric design, digital fabrication, BIM, and design to robotic production. He is also here today with Dr. Geneidy. Dr. Geneidy is a professor of materials and manufacturing and the chair of the mechanical engineering department at the American University in Cairo. She is also the University Senate vice chair and a formal Senate chair of the Faculty Affairs Committee. She's the founder and director of the Nanotechnology Master's Program at AUC. And she's the founder and director of the Additive Manufacturing Centennial Lab. She has received both her bachelor's and master's degree in material science and engineering at AUC and has received her PhD in mechanical engineering in the materials field from Texas A&M. So I'd like to welcome them both and happy to have you with us today. The stage is yours.
Thank you. Thank you so much, Reem, for the introductions. And thank you, Digital Futures, for having us this year for the second time, actually. Last year, we also had another interdisciplinary workshop together with Professor Geneidy as well, discussing the potentials of robotic manufacturing, additive manufacturing, and robotic 3D printing. This is our second year to hold this workshop. We have introduced a bit of changes to last year's. We added metal versus clay, because we are actually collaborating between two labs, the Additive Manufacturing Centennial Lab, which Professor Geneidy is leading, which specializes more into wire arc additive manufacturing, and also the Robotic Fabrication Lab housed at the Department of Architecture at AUC, more into ceramic-based materials and clay and so forth. Our collaboration actually started with a bit of a larger picture goal between the two departments, the mechanical and the architectural departments, primarily actually looking at how we can use additive manufacturing robotic systems as a clean process in the construction field, utilizing both metal-based and ceramic-based materials, coupled with methods of computational design and robotic fabrication, with the purpose of creating innovative architectural designs and structures. We are working on developing several prototypes for building facade panels and other structures, using sort of with a cleaner production agenda in general, so that we kind of mitigate any negative environmental impacts on the process. Second. So for this workshop, it's, as I mentioned, it's a hybrid interdisciplinary workshop organized by both of our departments, Mechanical Engineering and Department of Architecture at AUC. We actually utilized both facilities of both labs. The Additive Manufacturing Centennial Lab, or MCL, utilizes cutting-edge wire-based additive manufacturing technology, or 3D printing, in order to provide means of manufacturing and renovation of medium to large metallic net-shaped parts and components. And it's the first integrated metal additive manufacturing robotic system locally here and regionally, playing an active role in the to kind of boost the Egyptian industry through key stakeholders in the industry. It uses mostly the wire arc additive manufacturing technology, which basically uses, of course, a gas metal arc welding torch attached to an industrial robotic arm, and generate parts through layer by layer deposition of molten metal wire through an electric arc. And the premise is it produces much larger components and much higher production rates with higher mechanical properties at lower costs. The robotic fabrication lab housed at the architecture department mostly works with, it has just been launched actually at the beginning of this year. And so this workshop actually was a really kind of successful, promising vehicle for us to kind of start our process and workflow, aiming at sort of boosting this mechanism. We're using both the robotic arm that we have at the architecture department has both plastic and ceramic end effectors and the gripper, and also in the pipeline a subtractive also manufacturing parts as well. This is the additive manufacturing Centennial Lab using the wire arc additive manufacturing. It has, and Professor Geneidy, please jump in at any point if you would like to explain more about the lab and its facilities.
Thank you very much, Dr. Actually, you're covering the whole thing very well. And thank you very much. It's hello everyone. So the additive manufacturing Centennial Lab started with the wire arc additive robots, which was based on building layer by layer whatever structure you have. And I was lucky working with Dr. Sherif on structural can be used in architectural applications. And then it was augmented with a movable table, which allows additional 2 axes to the 6 axes of the robot. So it provided an 8 axes flexibility of motion and building, and facilitated the non-planar depositions to start with. We also added a 3rd robot, which is the subtractive robotic robot, which is 6700 IRB system. It also facilitates either integrated process of deposition and surface finish of any parts, whether again architectural or mechanical components, or it can engrave in solid parts, whether it's metallic or wood or ceramic, creating whatever shapes that are required by the design made. So this whole system we're very proud to have, and definitely it's adding an edge to our work, especially in architecture applications. And I would like to thank you, Dr. Sherif, and give you back the floor. Thanks a lot.
Thank you. I think the collaboration itself was really interesting and exciting because we were looking both ways. We have been learning as well from the whole arc welding process and how it could be kind of informative in the kind of structural kind of components rather than only mechanical parts. So that was really educational for all of us actually. And since last year, we've been investigating the use of WAM in architectural and structural applications. And it's been quite an enlightening experience, especially last year when we started the whole process. A lot of engaged participants who were actually looking at the same kind of edge in terms of this integration and interdisciplinarity. And so we also decided this year that we're going to kind of couple that with how we work with other materials as well, ceramic-based materials, clay and the like, and hopefully expanding to other materials and sort of working together on reinforcements or additives to clay and earth materials and so on, moving into this kind of cleaner production scenario and sustainability, especially in this part of the world where we kind of need more of use of local sources, local materials. So that's where we're kind of just starting to investigate and explore. And this actually workshop was really the start of the spark of this whole thing and the vehicle for doing that. This is the robot that we have at the architectural department. Now it's also an ABB IRB 6700 model with a 3.05 meter reach and a 175 kilogram payload. We've been just experimenting, as we mentioned, just launched this year. So this workshop really was the kind of the spark of that work. This is the team that has been working on the collaborative sort of interdisciplinary workshop. Professor Geneidy, Professor of Materials and Manufacturing, and the director of the Additive Manufacturing Centennial Lab, and myself, and our brilliant team of assistants and instructors, Omar, Geneidy, who I think you will be seeing his workshop just after this one. He has been involved in 2 workshops this year. And also Ahmed Al-Sukati from the Mechanical Engineering Department, as well as Islam, Salem, and Ali Ibrahim, research assistants at the Architectural Department. They've been really instrumental to making this workshop a success. And we're always happy to work together and collaboratively. The objectives of the workshop, we really went through concepts, techniques of both 3D printing in both the metal world and the clay world, in a way, principles of WAM and also robotic clay 3D printing, not in a comparative way, but really looking at kind of the design considerations, the main principles here and there. We actually kind of gave also the participants a bit of flexibility in choosing where they want to head with their designs and models after kind of taking a bit of background information about the processes and the concepts involved in both. The primary objective here was to actually design online and hopefully fabricate in our labs sort of some formal kind of models, artistic forms, both in metal and clay, or whoever, whichever preference, but really focusing on the idea of specifically non-planar kind of 3D printing, where we get to investigate more and more the non-conventional kind of depositing in a way in both techniques. So it's not the usual kind of stacking in a planar direction, but really going into the sort of working with different parameters and design considerations so that we can work with kind of non-planar directions and different angles and with different kind of speeds, and work with all those kind of technicalities to produce that and look at and explore kind of what can sort of come out of that process. And so our outcomes were basically looking at, as we said, robotic 3D printing in both WAM and clay, the design principles, and robotic programming and simulation using Grasshopper, and specifically the parameters and operations in WAM as well. Clay. Our workshop spanned about kind of 7 days net, actually, but it went, we had to use the breaks in between so that to allow participants to kind of work on the design itself, and first of all to brainstorm about ideas and their designs, and then another break to kind of go through robotic programming and come back and present that. So there were kind of 2 intermittent breaks in the middle, a total of 12 or 13 days, but an actual 7-day workshop tutorial and sort of progress presentations and so forth to look at issues and to look at specifics of the workshops. And this was our project brief, primarily to design a modular cladding panel to be manufactured either in WAM or clay, with some design considerations and dimensions related to the kind of time as well, and the kind of practical time of design and fabrication. We also, of course, had issues with time, metal and clay together. Of course, there is a big difference in terms of the time of printing itself. So we had to put that into consideration a bit. We had lectures, tutorials, projects by our participants. And of course, the aim was to physically fabricate some of these prototypes. And that was a learning actually process for us, going into the fabrication process on our end as well. We had 17 participants in total, representing 9 different countries. And those who actually made it through kind of complete projects, which we also went to fabricate as well. Most of those were 7 participants. These are just some samples of participant projects using poly surfaces to design and fabricate a metal part in the additive manufacturing lab. Also, so this is a module from this facade panel, and how this can be done using the arc welding technique, doing the robotic simulation. So this whole cell representing the simulation in the AMCL lab, and producing this model using the metallic 3D printing process. Another project as well looked at the process in clay as well, and the deposition, but how to kind of gear that towards also a non-planar process, where how the sequence and the detailed operation does not go just in terms of a conventional stacking of layers, but also, and maybe we'll see that into the fabricated outcome at the very end. So again, this was the deposition sequence and the operation related to that. And the another sample as well. Just a second, this work. Also looked at, we had a very enthusiastic participant who works with different models, doing some iterations, basically, and variations for different parts and panels, also using the same kind of technique on non-planar. So as you can see, how the surfaces do not end up with a just a flat effect, but also has this interesting aspect of, and of course, as you know, it has to go continuously throughout the whole effect, so that it kind of makes this continuous planar effect at the very end. Again, another similar project. The idea here, of course, was to develop one module, and then we would work on fabricating that module or a combination of those to make kind of a cluster or so. So this would feed into a larger sort of facade panel composition. Of course, what was out of scope here is to kind of look at the connections between the modules, but here how to visualize this in terms of, for example, if this is a facade module, then what is the effect of, from a design perspective as well, what is the effect of this non-planar aspect in terms of depths and extrusions and shading and stuff like that. So that was kind of the one of the implicit goals as well. We went on to kind of fabricate as well some of the designs that we had. So you can probably see the effect on the bottom left there of this non-planar effect, where the whole kind of layer goes into. Of course, there was a lot of challenges related to, first of all, the viscosity of the clay, for example, when we're talking about clay, and how, and the speed as well, different parameters that affect that. And of course, structural stability was a main challenge, because you can, and thickness, of course, of the layer and the nozzle diameter and all of that, because at the end of the day, you can have a successful sort of consistent layering, but then you would have a structural challenge with the overall height and or thickness. So you would have to have a double wall or a triple wall sometimes to do that. So the issue here was how to go and kind of optimize that in a way, or reduce waste in a certain manner. These are other examples of some of these units, and reaching that was actually through a lot of iterations, actually, with some failures and interesting failures and successes. And we also kind of went to test some of these after burning the clay into outdoor environments, and look at scenarios of how we can sort of merge these together or develop clusters out of these, looking at shading patterns as well in the exterior, and how sort of the scale of these can also, the impact of scale on these units and so forth. So the ultimate sort of scenario out of these units and other metallic components as well that were, of course, they had to take a lot of time in terms of the fabrication. So clay was a bit easier in terms of a handy fabrication process. But as well, we had experimented a lot even through last year with a lot of structures with metal. But the challenge was always, you know, if we were going to have a large scale kind of impact, what about the joints? What about the connections and so forth? And we developed some joinery and connections, but also there was the challenge of how these fit together, maybe the weight of the units and so on. So definitely, as we said at the very beginning, the whole aspect was related to challenges and some limitations that we learned from, and how we can probably introduce some reinforcing or materials or additives that would definitely add to the structural stability, and working on different scenarios, variations, weights, depths, and so on. That would create an interesting kind of paneling system and so forth. Geneidy, if you would like to add anything to this.
No, thank you very much. Again, I think you've covered it all, and looking forward for more collaborations and to your questions. Thank you very much.
Thank you. Thank you very much. And thank you, Digital Futures, again for hosting us. And hopefully we continue this culture in the future. So, thank you.
Thank you. Thank you, Professor Sherif.
Thank you, Dr. Sherif. Thank you very much. Very interesting outcomes. I will now move to the next presenter, which is Omar Geneidy, but unfortunately he cannot be with us today. So I'll be sharing his pre-recorded presentation after the introduction. So Omar Geneidy is an architect specializing in digital design and robotic fabrication. He's also the founder and manager of Geneidy Studio. He's a robotic programming expert at the AEC Additive Manufacturing Centennial Lab. He has worked as a research assistant at École Polytechnique Fédérale de Lausanne in Switzerland, and he's working on multiple projects involving robotics and digital fabrication. He has received his master's degree in robotics and advanced construction from the Institute for Advanced Architecture of Catalonia, and he has participated in 7 international workshops in his field. So I'll be sharing his presentation. Can you see it? Can everyone see it?
Yeah, yeah.
Hello, everybody. Thank you very much for the invitation. It's such a pleasure to be part of Digital Futures annual workshop event for the 2nd year in a row. As you can see, I wasn't able to make it to the event today due to family commitments. That's why this is a pre-recorded presentation. However, I will be following all of the discussion on YouTube after the event video is uploaded. And you can always reach out to me on LinkedIn if you have any questions. I will be presenting quickly now. Let me share screen. Okay, so I'll be talking about introduction to robotic programming using grasshopper workshop that was conducted in Arabic. It was organized by Geneidy Studio, our studio, and Geneidy Academy. I will first let me give a quick brief about Geneidy Studio. So in Geneidy Studio, we are a Cairo-based architectural studio established in 2020. We specialize in parametric design and digital fabrication. We are 3 main founders, myself, Mustafa Hashish, and Ala Al-Baroudi. and we have a team of designers working with us, and we operate in multiple countries around the world. We mainly specialize in robotic services and mass customization services and design for fabrication services. So to give you like a very quick brief about that, so robotic services, we design parts, we give assistance to companies working in the creative or construction industry by designing parts for them to be fabricated using robotic fabrication. We also do programming scripts, robotic simulation, robotic fabrication files, and our expertise spans across WAM, concrete printing, clay printing, milling, and other stuff. These are some examples of projects we did with our partners. This is a house in New Zealand, and other examples of projects that we work on with our partners. We also, as I mentioned, we collaborate with AUC, AMC, Lab in 3D metal printing. So we designed this table to be 3D metal printed. We do robotic simulation videos. We do mass customization, which is like having customization experience for products to be configurable. An example of that we did in a project in which we designed 10,000 different houses automatically to be used on Metaverse. We did an automatic house generator for that generates these houses and makes renders and makes 3D files for them and exports all of those different houses together. We also do design for fabrication, which is design for digital fabrication, and we did a number of products, design them so that they can be digitally fabricated. So our aim was to start transferring the knowledge we have publicly and the experience we have as a team. That's why we did Geneidy Academy. We launched Geneidy Academy. So Geneidy Academy, it's the academic branch of Geneidy Studio, as I said, and it's a non-for-profit organization. Our mission is to provide free, high-quality content in Arabic. Those contents are provided by Geneidy Studio team or by partnering with experienced individuals in the Arab world. So the type of contents we do through the Academy are courses, workshops, lecture series, interviews, and we do it in multiple tracks: robotic in architecture, digital fabrication, parametric design, environmental and sustainable design, Islamic and Arabic architecture, architecture visualization. And we have a platform. This platform is this YouTube channel, which has now over 62 videos, all available for free and in the Arabic language. For those in the contents that we did in those topics, we also have a group that we call Geneidy Academy Community. It's a place for instructors and students and interested people to join and discuss the outcomes of the workshops, discuss projects, share resources, share job opportunities. And it has been active so far since we have launched it about 3 months ago. So the content we have, it starts from Rhino course, Grasshopper course, all in Arabic. And then our workshop at Digital Futures, which is now available on the Academy, and which is what I will be speaking about. So this workshop, it was 6 days workshop, 12 hours of teaching. It had 20 to 28 active participants on Zoom. We also received a big number of applications. That's why we added an option of live streaming on YouTube. And it was joined by ranging from 40 to 60 active participants as well. And we tried to have those people on YouTube have the same experience as the people on Zoom. That's why we use the Facebook group to answer questions, to share resources for both type of participants. And the workshop had a number of lectures starting from Introduction to Digital Fabrication, Robotics in Architecture, Robotic 3D Concrete Printing, Introduction to Industrial Robots, and then speaking about opportunities of 3D concrete printing industry in the Arab world, as 3D concrete printing was the main focus of the workshop. We also had tutorials about designing 3D concrete printed walls using Grasshopper, advanced data tree using Grasshopper, robotic programming in Grasshopper, and robotic simulation as well. We invited a number of guest lecturers. So the first one was Mr. Edward, who is the CEO of Tam Vinci, which is a 3D concrete printing company in UAE. He spoke about the industry in the Arab world and the Middle East, and gave a lot of insights about the 3D concrete printing industry. Also, Engineer Ali Magdi gave a tutorial about Grasshopper in design tutorial. We also had Ziad Zain, Engineer Ziad Zain, who is a local 3D concrete printing expert, who gave also another interview presentation about the industry. We had also internal guest lecturers from Design Studio themselves. So we had our three of our engineers, Engineer Team, Engineer Ruwan, Engineer Fatma, who gave a number of tutorials inside the workshop. So the outcome of the workshop is that we have so far about 25K total views of the workshop videos to date on the YouTube channel. So it's still, people are still watching the workshop as we speak. We have about 10K total watch hours of the workshop videos. Participants submitted 8 projects during the workshop. And then 4 extra projects so far have been submitted from people rewatching the workshop on YouTube. We also provided 1 training opportunity for one of the participants to work at Design Studio. These are some samples of the projects that our participants submitted. Those are all, like the submission consisted of doing a poster, grasshopper file, simulation video. So those are different projects that were submitted during the workshop and after. There is a small video that shows the different submissions. I can show it. So this is a project by Model Su'i. It was a bench and a shed, and he did the robotic simulation video for it as well, and also another project by Daubmann. Also a shading element, kind of a shading element. And then this is a joint project between Nazim and Mahmoud. So they did this Arabic-inspired pavilion, 3D concrete printed one. And then this was one of the projects that were submitted after the workshop by Ahmed Nagar, was about designing this concrete column and doing the fabrication files for it and the simulation video for it as well. And those are some renders. This is another project in which the participant showed how multiple pieces can be printed together using a track, utilizing a robot track. And then Yasmin, who was a master's student, and then took what she learned from the workshop and started applying it on her master's project, and did this simulation video and submitted it after the workshop. And then also another example from Sara Sami for designing and printing this wall sample with the infills and everything. So this was actually not just the end of this track. We also did another lecture series to complement what we did in the workshop. This time with engineer Luay Kurdi from Print4D, the CEO of Print4D, also in UAE. This lecture series will be published on the Academy very soon. And also another lecture done about 3D concrete printing, and a whole introduction about 3D concrete printing, and will also be launched on the Academy very soon. We also did other workshops on the other tracks, which is now published, like this one, about fundamentals of sustainable and environmental design, architectural design by engineer Ali Fahmy, who had a master's from the AA. This is, I guess, 10 hours workshop, and there's now available also for free on the Academy YouTube page. And we will be doing more. You can follow us on Facebook, LinkedIn, Instagram, Jazar Academy or Jazar Studio. And we're looking forward to doing more content and collaborating further with Digital Futures. Thank you very much for the invitation.
Okay, so that was it for Omar's workshop session. Very interesting outcomes. And now I'll be introducing our next presenter, Mohamad Hanifa, who's also joining us today from Portugal. So Mohamad Hanifa is a PhD candidate at the School of Architecture of the University of Minho in Portugal, awarded by the Foundation of Science and Technology. He holds Masters in Advanced Architecture by Polytechnic University of Catalonia and the Institute for Advanced Architecture of Catalonia. His thesis titled Clayfen was towards creating sustainable wall system to replace heating systems. He also holds a postgraduate diploma in open thesis fabrication in Barcelona with dissertation projects on earth architecture and infrastructure for 3D printing and architecture. He's also a research assistant at Lab 2PT and a junior researcher of advanced ceramics at R&D Lab. And he has received his bachelor's degree in architecture engineering from October University MSc in Egypt. He specializes in different fields, including architecture, additive manufacturing, coding, and digital fabrication. We're happy to have you with us today, Mohamad. Thank you for being here. The floor is all yours.
Thank you so much, Sherif, for your introducing me. Thank you all for your amazing presentation. I'll start right now to share with you my screen. Okay. Sorry. Okay, hello everyone. First of all, I would like to thank you for this opportunity to share with you the outcomes of the workshop. It was like for 1 hour. It was like interactive workshop between me and the students to share knowledge and experience with additive manufacturing with earth and earth-based composites, and trying to explain computational methodologies for defining shell envelope systems. So basically, I will just start to speak about the goals of this presentation. Is just talk about three goals. First of all, about the materiality and the machinery, and the final goal, it's about design methodologies for defining shell envelope systems. So basically, the workshop, it was about introducing the students about simple prototypes, how we can start print with the clay, basically without any additives. So first of all, I started to talk about the cantilever and earth architectures, cantilever with support, without support, and printable support. So we were talking about simply additive manufacturing technology with clay. Then after that, we started to talk about how we can add different kind of supports, like with other materials, like wooden supports, how that would affect on the some difficulties with printing, especially with earth, buckling, cracking, shrinkage. So we were talking about different parameters that we could face through the printing process of earth-based composite materials, and it's also clay. But later I'll talk more about earth-based composite, not just clay. So basically, we were talking about the material issues, the difficulties that we could, the problems that we face through the printing process, and also the scale. Basically, when you print with the clay, we thought that we could, the scale, it's a main issue, especially when you print with the clay or earth. So then after that, we were talking about this system. And when we add other supports from other material, it was like efficient way, or we could find other issues. So basically, that's the main topic that I'm trying to develop in my thesis. And also, I was sharing with the students in the workshop. So mainly it was like more about interactive workshop to share knowledge between me and the students, and also to introduce the students about these fields, and also to share questions and inquiries about this kind of technology and materiality, and this and also sustainable architecture. So after that, we tried to talk about how we can develop a specific composite that we could solve many issues, especially 3D printing earth-based composites. So mainly now in my thesis, I'm studying two types of clay. Clay it's from Spain, Barcelona, and also clay from Barcelona city here in Portugal. It's very famous with stoneware clay. And then we were talking how we can add specific additives like natural fibers, and how that could affect the material behavior through the printing process and after drying time, and also studying earth binders, especially sodium silicate and sodium hexadimide phosphates, and how these hydraulic binders could affect on the material composite itself. And also for sure in correlation to the amount of water, because mainly the main problems that we've talked about, and through my experience with printing with earth, mainly you're facing cracking issues after drying time, specific time, and also after adding different kind of fibers, the printing process getting very hard, especially if you are working with specific extruding system. So like there are different kind of extruding system. I will talk also about it because it's part of the machinery process. So basically, at the beginning, we'll talk about different issues about the material science of earth-based composite. What is the best formula, that we need to reach in order to correlate, can say, the numbers of the formula between the amount of the earth into the hydraulic binders, and also into the amount of the water, and also for sure the amount of the natural fibers that we could add. So mainly after that, I was talking about what specific tests that we need to do in order to test the amount of absorption of the water of the natural fibers that we could add to the composite, and also about the extrudability of the material, how, for example, how that could affect, like, I mean, once we add more fibers, we will face more difficulties in the extruding, which is so different from extruding only clay, or especially stoneware clay. So basically, I was talking about the differences between the stoneware clay and earthenware clay composites, and how that could affect, especially if you want to print something in the construction site. So we were talking generally about this, and I was also sharing my findings that still in the humble phase, you can say, in the first year, after that, I was sharing also the extrusion system that I was using by using 3-axis machine only, because I feel somehow it's more correlated the construction side. As you know, like the most famous company that we are working in this field right now, this WASP company, and they have a crane system, and especially it's like 3-axis machine. So I didn't talk much like about the robot, like, adding more axes, because mainly I was trying to connect them about the reality in the construction side. So basically, when we work with a 3-axis machine, and you can say planar 3D printing process, we'll face more difficulties, especially when we print something with more cantilevers. You can say within the layers you have more buckling issues. So I start talking about the simple surface of geometry, like the simple dome, if we want to print it with two types of clay with different, like with this 1 to 10 scale. So basically, I was talking about the difficulty with printing composite with a straw. It was kind of, for example, according to the tool that we have in our lab for the moment, but now we are developing also extruding system to print composite with sisal, which is more difficult, but will help more to prevent problems with buckling issues, and also will help more to do bonding between the layers that we print, and also will help to reduce the failure with this kind of geometries. Like so basically I was trying to explain how we can coordinate and organize the amount of the fibers to the binders to the aggregate for sure, and also amount of the water according to specific findings and tests I'm doing through Advanced Ceramic Lab and Geneidy in Portugal. So after that, I was talking also generally about different kinds of extruding system and how that could affect the extruding process, especially if you want to print complex geometries on the construction side, which is something not really reached right now, until now, but I will talk about a researcher actually later. He read some part from this research. He printed kind of complete roof with concrete material, not with earth-based composite, but I'll talk about the computational methodology that he developed through printing process. But mainly I was talking also about the students, about the pneumatic systems, and mainly it was really working worthy with the concrete materials. Because also I have a colleague of mine at our lab, Advanced Ceramic Lab. He's also developing a PhD thesis with 3D concrete printing. So he was studying the differences between the extrusion systems for different kind of composites, or different kind of, you can say, plastic materials. So basically we developed specific extrusion system, and we found out after different tests, actually it wasn't really perfectly working, and so for that reason now we are developing another system. It's linear activator system. It's more applicable for earth-based composites, but still I don't want to share with you now. Actually the results still in the progress, but now you can say the main goals of the last workshop, I was talking about mainly about design methodologies for 3D printing shell systems. So basically, I was trying to connect these methodologies with Asian traditional building methods. So I was trying to explain for the student how we can extract these methodologies, building with masonry, and how we can you can say mimic these methodologies to the 3D printing process, how we assemble the Adobe breaks in such a way in order to build self-supported systems, and how we can translate this to specific methodologies for 3D printing, and through the 3D printing process without adding any kind of support. So in this video, you can see how we kind of use specific methodology, especially it's extracted from Hagia Sophia. So you can see specific bentative elements that we are spreading in such a way in order to support the whole dome through, I think, Hagia Sophia Mosque in Turkey. So basically here we're using like 1 to 10 scale, and also it's 3-axis machine. So it's basically, you can imagine this in construction site, you know. So for sure in the larger scale we face more issues, but for that reason I was explaining this in the workshop for the students. And Okay, so mainly, as you can see here, the design methodology of you can say of this prototype is extracted, as you can see, from bindative elements from like Asian historical logic. So it's like mainly it's about organizing the mass within the shell surface and trying to increase, you can say, the inertia within the geometry. So basically, I was trying to explain how we can develop this methodology with other methodologies in order to be more stable printing process. But for the moment, in this composite that I'm using, mainly you can say only stoneware clay, okay, with the aggregate and a lot of amount of sand, without fibers at this moment. So basically, also I was explaining a lot about different problems that we could face through the printing process. As you can see, how we can control the central gravity of the shell surface and how we can prevent the buckling within the layers, and also how we can extract correction or issues that could help us in the printing process from the Asian traditional methodologies, with building with the bricks. So you can see here, after that, I was trying to explain if we started from simple shell surface and how we can increase the thermal, you can say how we can increase the inertia of the shell surface of the geometry by increasing the amount of mass by doing a rib system, as you can see here. So basically, I was explaining about this methodology and how that could affect in the printing process. So mainly also, if you want to do a printing process for shell geometries, you need to design the sweep line with different angles. So for the moment, I explained only about the minimum one. So basically, as you can see here, I was explaining about how we can control, you can say, the global inertia of the geometry and how that could affect in the printing process by doing some simulations of overhang angles before the printing process, and to see the results in small prototypes for the moment. And how we can, for example, extreme the process by printing only half shell, so that displacement would be more extreme, but we will know, for example, this type of surface without any rib system, how could affect after adding, as you can see here, more small masses within the surface. So it was like more stable in correlation to the others. So mainly the general aspect was about how we can design a way that help us to prevent problems in the 3D printing process of earth-based composites, or you can say stoneware clay with other additives. So as a result, we need as a researchers, always we trying to correlate our findings to specific formula. So there's basically, when we start the surface area, it's really critical parameter. So the more we add the inertia within the shell surface, we will have more stable printing process. And if we multiply this by 10 times in the real scale, so we'll understand more how much we need to add amount of fibers also to prevent the buckling within each layer. So we were talking about this, about this formula and how that could affect in the future process, I mean, in the construction side. So after that, we talked about another methodology, also inspired from traditional methods, and also how we can control this methodology in order to print different iterations of shell surface, how that could affect, to build other levels of the shell. So mainly until now in printing process, we have always problems with printing complete roof. It's really critical for the moment because of buckling issues. If you want to print something without any formworks and without any supports. So for that reason, in this research, which I feel it's really interesting for 3D printing, especially with sustainable materials of the future, how we can like provide more efficient process by reducing amount of the materials, and how we can correlate it for the, you can say, the design methodology of the shell surface, and how we can correlate it to the design of the tool path itself. So I think as Dr. Sherif, he shared something about non-planar 3D printing process. So basically it's also another methodology. We were thinking how we can control it in order to increase the density within the surface itself, you can say, of the shell. So we will have more inertia at such points of the surface itself. So we will have more stable printing process without adding, you can say, more masses within the surface. So is another methodology related about the computational methodologies or computational aspect of designing the contour path itself and the slicing method itself of the shell surface. For the moment, also we are studying also another methodology extracted from also from ancient methodologies of building with Adobe, or you can bricks, and how they were, for example, you can see how they were designing out the surface itself, the distillation topology of the surface itself in such a way to all, you can see all the systems supporting each other. So, okay, we were thinking how we can translate this, you know, to as a element or parts could support, you know, you can say the surface of the shell itself. So, okay, we found out we could do like such elements could, you know, combine with each other. Like it's like just for the moment, it's conceptual aspects we're trying to study and translate it to the ancient building methods. As you can see here, there is a lot of project I did also at IAC. So it's like about modular wall system, also by using only, you can say, earthenware clay without any additives, you know, without any fibers, you can see here. But we were studying also the you can say, the cantilevers of the corbels within like a system like a wall, and how we can add other materials, you know, like roofs or pergolas, like, you know, to this system. But in my thesis for the moment, I'm thinking how we can build a complete, you can say, complete system wall with roofs, or we can say a complete shell without any support, without any formworks. So that because of this, like, I'm trying to understand the results from my old projects, and I was explaining to the students, and I was also saying, like, you can say it's this workshop is more informative about this kind of materials, sustainable materials, and this technology. So here you can see how we can control the slicing process and how that could affect, you can see this is like a simple method, but you can see how that could affect on the ends of the printing process, and how that could affect, you know, on the layer itself. In the, like, imagine this in small scale, imagine in the large scale what we could face. So basically this, like, prototype, it was like just from stoneware composite, but the main idea, it's about like how we can merge all of these methodologies, you know, as I explained before about the modular wall system, and also explained about the design methodologies of shell system, like with the RIP system, and also without RIP system. So that's the idea. We're in this thesis, we're trying, me and with my supervisors, I'm sorry, I didn't explain in the beginning, Bruno Ferrero and Paulo Mendoza, they're my coordinators in this PhD thesis. So basically we're trying with, and actually now ongoing, 2 research papers for 2 conferences in Barcelona and also in Madeira about building materials with the sustainable materials, also about design methodologies for building complex geometries like shields. So this reference actually for Sandy Cruz with concrete material was really interesting for me now to also to share with you, because also we are trying to understand how this methodology worked really well, you know, with concrete material. So basically it's about a correlation between programming with Python, trying to understand how we can slice the surface in such a way, non-planar 3D printing methods, in correlation to coding, or we can say scripting. So basically what I understand from this reference that mainly the code is understand the design of the surface itself, and he trying to do a slicing method to control the layer height or the layer thickness in such a way in order to build stable, you can say, printing process until the end. And also I was talking about such important part, you know, if you want to print a complex shell in the construction side, you need to think about the thermal conductivity, and also about the characterization of the space inside the shell. So basically we need to think about the infill design system, because not about the structural performance, also about the thermal performance of the shell system itself. So basically also about, I was trying to explain how we can control this kind of system by increasing, studying the density as such a part of the shell system, and how that could affect, you know, also on the printing process and stability of the geometry itself. So what then I was talking about the general scope. It's to merge all of these methodologies from materiality, from machinery, and also concentration, more concentration about design methodologies for 3D printing a complete, you can say, modular shell system. You know, because at the end we want to also to think how we can integrate this, for example, for neighbors or habitats. So also was such a concept also for a futuristic concept, you can say, for my thesis for the moment. And I would like to thank you all also, most of the foundations that now I'm working with them, like University of Minnesota and the Ceramic Lab, also Foundation of Science and Technology. They're supporting and funding this thesis and this research, and also Lab Tupete in correlation to Professor Bruno and also to Professor Bruno Ferrero and Paulo Mendoza. And this is the end of the presentation. I would like to thank you all.
Thank you, Mohamad. That was a great presentation. I think I personally have a lot of questions to ask you, technical ones. So maybe we can have a chat later. So without further delay, I want to invite the next 2 presenters, presentations, which are going to be from the Spanish language channel. So let me just give a very quick introduction to Edurne or Edun, who has dedicated her career mainly to design solutions for fabrication of complex designs through the use of computational design, material research, and process development. She studied architecture in digital fabrication in ETH and at Tecnológica de Monterrey. She has participated in projects like Mexico City Airport, Clay Rotunda, Magic Queen, Venice Biennale, and currently in development of the fabrication process based on the endless filament winding at Luxembourg. So I would like to give you the platform. Yeah. Hi.
Hi, thank you.
Yeah.
So I'm presenting on the workshop that we gave. this summer. It was taught by Dinorah Martinez Schulte, who couldn't be here. She's now printing some stuff for an exhibition in Mexico. And myself, we are both co-founders in Manufactura, which is a company that's specialized in digital fabrication through different processes, together with multiple analog processes, all towards design and architecture implementations. The participants of our workshop were Claudio Feldman, Felipe Villanueva, Matias Dalla, Ángel Salazar, Julia Veras, Uri Luis, and Stefania Cavalier from different parts of Latin America. And as an introduction, our purpose was to create a space for reflection and criticism of between the analog methods and the digital fabrication, and to explore which are the conditions of each and how they can merge and be manipulated to create new designs and to have new opportunities and advantages. So our process was to take different objects, scan, learn a bit about scanning methods, about the software possibilities we used mainly Rhino for creating the meshes that were done for this workshop. And we saw a bit of robotic fabrication and digital fabrication with 3D printing. So some of our cases of studying were this totem, which we made in Manufactura. This was a lighter totem based on 4 different rocks that were picked from different parts of the world. Some were from Spain, some were from Oaxaca in Mexico, some were from Morelos. And here we wanted to explore this possibility of taking something from its own environment and into the digital world and then manipulating it so that it had a completely new life in another environment and for another purpose. So here are the printed parts. And here is when they were getting printed. Another example was the Mo canvas, in which Dinorah worked in Ensemble Studio. And this was based on multiple pieces, which then were applied to furniture. And they were done with these textile pieces that were covered in concrete, and then reshaped based on different objects, so that they took some of the materiality of the object itself, and they were manipulated mostly by hand. And then they explored this opportunity of having the physical object and then transforming it in the digital world and fabricating it through different layers of, in this case, wood. And then of the possibility of taking that digital design and going back to the analog by manipulating it physically. We also talked about clay rotunda, in which I participated, and well, the process was developed by the MEAS team of our generation. We both studied in ETH, and this process was based on multiple pieces of wool that were then turned into bricks that were compressed in order to recreate a monolithic piece. And this process is based on this robot that is a mobile robot which takes the wet bricks and compress them in the place that's assigned digitally. The robot continues moving as it finishes the sequencing. And one of the reasons to have these sections was because of what Mohamad was mentioning of the clay breaking, cracking due to the loss of water content. So in order to avoid that, we decided to make these sequencing. And also because of that loss in water, there were a lot of shifts in the movement. These were some of the analyses done during the MAS. And for that, we were adapting digitally from what was happening actually in the physical world. Here is a scan of the final mesh and one example of the pieces that were done. Another example was the application on robotic fiber winding that I'm currently doing in Luxembourg at Gradel. And we're working on these windings through multiple bushings in order to create, to have the possibility to vary a lot the physical opportunities of the piece.
I talked to my doctor about that.
And we are currently using the scanning methods to test for quality reasons. So this was another application of the methods we were seeing. And final one for this presentation was the opportunity of manipulating the physicality of a whole object through the use of meshing and different types of subdivision. In this case, digital bamboo, which was built up in Zurich and after in Venice Biennale. And here, all the mesh was based on one mesh in Rhino, and it had different layers. A bottom layer, which was the structure of bamboo, and the top layer, which was based on a textile, mostly based on nylon. And these are some of the variations for the structure. And here you can see the subdivision applied through the textile. So we also explored different applications in other disciplines, such as scanning pieces to create records for historical pieces, or scanning for quality management, even for dental pieces or for crime scenes. And also its application in other design and art possibilities, like the scanning of the favelas in Colombia, or the scanning of faces in order to test glasses, or turning art pieces into furniture that Sebastián Nerasuris has done, or even these like walkthroughs of Taliesin West. So we started by scanning pieces. Everybody scanned different pieces, and this is an example of one of our students. And he decided to scan a rock, and most of his exercises were based on this very particular rock. Some others decided to base on something more liquid, like foam. or on pieces that were found from different places in the streets. We also saw a bit of mesh management, topology optimization, and mesh forming, and mesh repairing. After we saw two methods for printing. First, 3D printing with a 3D printer, and 3D printing with a robot. And based on this, the students started their processes. So the workshop was divided in 3 teams. The first one decided to take these objects that are considered trash from the streets and manipulate them. Afterwards, they also tried with printing the pieces, or with testing the wax on surfaces and manipulating the meshes, or taking pieces of real world or natural pieces like the rock and then reshaping them with clay and remaking the process digitally. So these were some of the results. They were all very interesting. This was based on shaping the wax of a candle using a glass, and they chose a glass in order to have the transparency of the glass and being able to extract the mesh of the wax. Then they manipulate it and they turn it into an exhibition in the plaza. This was the other team who was taking the trash scanning. They manipulated this mesh and added different types of subdivision and movements. And these were some of the explorations done by the team who chose the rock. And they started applying different types of textures based on the mesh that was formed from the scanning. So yeah, this is just a small video of the processes of each team. And we really like this theme, especially for our teaching in Spanish, because it made sense for the Latin American environment in which the accessibility to robots or sometimes 3D printers is not so common. And we're shaping the stuff by hand, and adding some of the craftsmanship to the processes makes a lot of sense. So this was basically our workshop. Thank you.
Thank you. I think you said something really interesting towards the end, but we'll pick on it. We're a little short of time, but nonetheless, I do want to make sure that we get giving enough time to our next presenter and the last presenters. So Yessica and George, can we have you both around? I'll just give a very quick. Yeah, hi. I'll just give a very quick introduction to Yessica, who is an architect and holds a master's in advanced architecture from IAC. She's a researcher and academic coordinator of architecture and urban strategies department at CEDIM. Her research focuses on integration of microorganisms, biomaterials, and environmental performance in architecture through computational design and novel fabrication strategy. George is an architect and researcher with a strong focus on robotic fabrication and development of innovative building systems. He is a winner of Touch Fair Architecture competition in 2011 and has a Master's of Science from ITech in University of Stuttgart. And he obtained both ICD and ITK, which he obtained from both ICD and ITKE institutes. So looking forward to your presentations, guys. Yeah.
Thank you. So I'm gonna share the screen. Can you see the presentation?
Yeah, yeah.
Yes, perfect. So our workshop was called Cavidades Progresivas. And for this specific workshop, for us was very important to show to the students how can we use these contemporary tools, not only focus on fabrication part, but also how can we apply this to the real world, and how can we propose something to solve our nowadays problems, mainly environmental problems. So this workshop was focused on integrating computational, material, biological, and building systems. So the focus of the workshop was to propose a project in order to talk about how can we integrate biodiversity in the built environment. So how can we enhance this biodiversity that is getting lost, especially in the urban environments? And we want to work on the integration of small species. And how can we do this integration, but talking about material integration, biological, and fabrication, especially robotic fabrication? This image on the right side is a result of one of previous workshops I've been teaching at school where I'm a researcher. And for us, it was like a starting point because in this previous workshop, we didn't manage to see the fabrication part, only like conceptually, how would it be, like this integration with the urban environment. So we were really interested on solving the fabrication part and the design part, and how this fabrication part will change the design strategy to be able to build this. And George is going to introduce us to how this fabrication strategy was affecting the design process for these pieces.
Okay, hi everyone. Well, basically for the global idea was to work with fabrication, robotic clay, 3D printing, as you want to develop vertical structures such as columns or elements which could be 3D printed. And we looked first about the fabrication constraints, which will involve the 3D printing, and the main part was the on and off control, or to work either with the continuous printing. On and off control obviously was probably the solution to our first design that was coming from the previous workshop. It was generated with the game life strategy. This was the ideal to generate this kind of porosity we were looking for the posting life. And it was basically we had to pass for a slicing, general slicing system to generate the control path. While the continuous printing was the solution to for the technology we had available, and we looked to a linear growth algorithm to generate the geometry. So, the next slide. Yeah. Looking into global design constraints, what we set as priorities was interior boundaries and exterior boundaries. The exterior were defined to actually to contain our architectural element, and the interior one will help us to develop or work on the integrity of the structural part. And the design intentions were to work on density inside and texture depth from the outside. The way we worked to actually to manipulate this strategy was the interaction between multiple input curves, and which were generated through physics-based simulation, and which each one had assigned a different density courses. And we had also, through time, we could interact and define and change them to make this interaction according to the user. So we can see here the first inputs or the first generation in 2D, the first explorations were understanding how the boundary, external and internal boundary conditions could interact, and how we could we have to control like minimal distance between curves to make the fabrication possible. Well, we can see a possible outcome where with the generation of the multiple curves one on top of each other would create this kind of density and interaction between them, and actually generate this type of porosity we're looking into. But we're looking at to have more control and not have a chaotic environment. And basically, starting from a simple curve, there was an really a linear deformation from simple geometry to something complex, which we were looking to improve, and also to generate a type of texture that would help to integrate this type of interaction with with small species. So these were the first outcomes, which were quite chaotic, but also useful in some sort, creating the type of cavities we're looking into. But the only thing is that they were having a really strong directionality from simple to more corrugated outside boundaries. So this we can see that still it was having a kind of density chaotic, which was well intended, and we could actually also control the thickness of this structure to not exceed with the weight and the material considered. The part that was actually the point of achievement was to understand that we could work with multiple curves, input curves, which each one could push each other and interact while the degeneration curve by curve was affected. In this way, we could avoid to have this directionality in the elements. So we could control the outside surface to create rugosity or this depth and texture only in specific areas in the direction of the column or the according of the needs that we wanted to integrate for the micro biospecies. So here's some examples of integrating additional texture to this global geometry. And well, I will pass the word to Yessica.
So one really important thing for us and why we decided to use this strategy is because we needed to look into different topics in order to integrate these small species. There are certain needs in terms of humidity, protection from wind, from water flow, and from constant exposure to sunlight that we needed to consider in the design. That's why this strategy was very useful for us, as we can see in this example of one of the projects of the outcome from the students. They were looking at how can we give a bit of protection to butterflies, because when they're traveling, at least here in Latin America, from south to north and vice versa, they need protection for a while, and while they're resting, and they need to be protected from the wind mainly and from water. Sometimes there's not enough space, especially in the urban environment, where they can feel this protection. So this structure was very interesting. You can see in the image on the left, the iteration that the students were making. They were very interested on generating these layers that we can see on the right image. This outcome that was giving them some sort of inner protection, outer protection, and we also were taking care of the language of the object, so we can see it also as an interesting piece, but that could be also working for this purpose. You can see a render. They were imagining having these objects in a park maybe, or places where we can actually find these butterflies. I think they're a bit out of scale, but yeah, this idea of having a different heights for different needs, it was very interesting in this project. And there is the second project that was also very interesting because it was talking about the deforestation in the deserts that also exists in Mexico. And we wanted to find a solution on how can we help to have this cactus growing again in the desert, but it's not only in the desert, also in the city, you don't see cactus anymore. So there's specific bacteria that is needed in order for the cactus to grow again. And this bacteria needs specific conditions that we were considering integrating in a ceramic piece that would work as a tree surrounder, like this metal piece that we can find around the trees in the city. This is a very, I think, forgotten element in the urban environment. We never look at it. So for me, it was very interesting how the students were looking at this specific piece and how this specific piece can help repopulate cactus, because cactuses start growing under a tree first, because they first need some shade, and this bacteria needs specific humidity and conditions in order to grow. And once this bacteria is present there, cactus can start growing. So that was really important for this project, because we needed to put this element under a tree. So the tree surrounders was a really good idea. We were also talking about what kind of ceramic we will use. We will 3D print ceramic, so we will use dry one and one that you will cook one time, and then the one that you have with the glazing. So these three kinds of ceramics will be used for this project because it will give the bacteria specific conditions in different stages. And we have some design iterations with this linear growth strategy, which was very interesting applying this project because we were thinking about the modularity. Even when the linear growth is a chaotic strategy, we were looking at how can this be modular and can be assembled in a way that will still look chaotic, but it would be easy to assemble, to fabricate, and to understand at the end. So some other design iterations, and you can see on the diagram, the lines, the layers that contain this version. So this is a conceptual render with the tree. Barely see, but we can see this tree surrounder here in the tree. This was the final proposal, the initial curves and the iterations. And at the end, how each of these layers will have different type of material, 3D printed ceramic, but with specific conditions, and it will work for different stages for this bacteria to be able to be present in order for the cactus to grow. Some of these ceramic pieces will disappear at some point. So we will keep only the first part of the ceramic. The other ones will disappear at some point. And I think it was a very complex workshop because we were talking about many different things, and we'll have to go to fabrication and then to come back and then see the material part and then come back to what the bacteria needs and then the cactus and there were different projects. But to be a 3 days workshop, I think the outcome was interesting. Might you have something to add here?
Well, unfortunately, we couldn't manage to reprint. There was a COVID situation on the last moment, but we are still planning to do the third part. And actually, it's important to mention that the workshop was made at three of us. Rodrigo Shordia was part of the development, also the code, and it was a collaboration between Selim, our university, and Anáhuac from Mexico City.
And I think that will be it. Thank you
Yeah.
very much.
Okay.
Thank you very much.
Thank you. Thank you, guys. I think some really great outcomes from this workshop. I think maybe it'll be good. I can invite everyone to just put on their videos, and also Sara is around. I have a question because Yessica, you guys are around. I think I can start with some reflections of all the workshops. We'll keep the panel discussion short because we're really running a little bit late on our schedule as well. But just few reflections, and maybe everyone can then just pull in their thoughts onto it. So I think what was interesting in your workshop is most of the workshop is the knowledge that you guys are carrying from a certain understanding of materials, right? And then sharing that knowledge in a platform of 5-day or a 3-day or a 4-day workshop, and working along with students. And my question to everyone is actually, where do we all see the teaching or the academics of robotic fabrication going ahead? So everyone's basically discussed a lot of aspects about fabrication. From Yessica, you guys are talking about biodiversity and built environment, and how can we use these new age tools to integrate into the existing built form, because those are very interesting questions, that we already have an environment which is full of so many diversity of things, and how can we intervene thoughtfully into that through our knowledge of computational design, or through the knowledge of robotic fabrication. I think before this, the presentation on real-time assessment of forms that were happening in digital and analog fabrication workshop. And in the same way, I think a lot of material that came out from earth-based composite work of Mohamad as well. I think you were constantly positioning yourself as a scientist and as a person who's working from a material science perspective, working with the clay, looking at the way in which you could 3D print, because you are also asking a really relevant question. When you are doing planar printing, you are using the right kind of tool to do that. And maybe in your conclusions, when you were talking about that you will go non-planar, that's where maybe the role of robot or robotic fabrication really comes into picture. And again, I think Omar also talked a little bit about how would you start teaching about robotic fabrication in an educational environment. Dr. Sherif is talking about augmentation of robots, which is very interesting. Here, you are definitely talking about some really impactful work, which is directly related to the industrial practice of plastering of walls. And of course, at Sara, you are constantly engaging with the robot through the idea of its tool parts. So we have like a good amount of work out there. And of course, today was a great discussion altogether. So I want to just have some thoughts on where do we see the academics growing with this aspect of learning from robotic fabrication.
I'm sorry.
Yeah, anyone can start. Yeah.
Could you please repeat your question? You mean what is the the goal that we could reach in the, for example, from robotic fabrication in the end. Like from my point of view, I think the robotic fabrication will integrate a lot with the construction side, like because I've seen like now a lot of companies, for example, in Texas and in Italy, they are building habitats by using robotic systems and different types of materials. So I think the robotic fabrication, like robotic technology, it's gonna be like the future of building, many things. But for the moment, I've seen like some companies, they're printing with concrete materials, like a complete habitat in Dubai. Also, they build like kind of habitat. Kind of gallery with the sustainable materials. But it's still in initial phase, because many difficulties, and I feel also the aesthetics parameter, it's also critical for the moment, because mainly if you check most of the project that they are doing still need, the contour crafting method. Still you have like, the aesthetics is not really complete if you compare, with building with bricks, as we used to, to build our building with it. So I feel there's a lot of things need more to develop with this technology and this types of plastic materials in terms of like concrete or earth-based composites or cement-based composites. But I feel like it's the future, because I feel we need to build more with less time and with more efficient materials, like more stable materials. So that's what I feel now, like from
yeah, of course,
what is happening now.
Yeah, of course. I think there are no two ways about it. Definitely, it is there. It is already present very much in the industry. I think what I want to also inquire a little bit about with you guys is your engagement with the students at your universities, your schools, or even in the platforms, in the workshop kind of platform. So how far do you see that research proceeding for or going ahead when you're working and engaging with the students and sharing the set of knowledge, the set of material intelligence that you have gained? How far do you see that going in the robotic fabrication aspects in your workshops?
I think, and we were talking about it during the workshop, that the environment in robotic fabrication we studied in ETH, so that reality is completely different to the one you can find in Latin America. There we were dealing with an on-site robot that it's kind of a crazy idea still in a Mexican environment. So what we're trying to do right now with Manufactura and Dinorah with teaching is trying to merge this possibility of handcrafting, because not everybody, like the builders or the people who are designing, won't always have this knowledge of how to make stuff completely fabricatable by robot, which has also a lot of advantages, like repeatability, like complying with some specifications, like quality aspects, and having this possibility of turning the craft or having the possibility of manipulating an object in reality and then turning it into something repeatable. We think that has a lot of potential, at least in that environment, which is different from the one we saw during our studies.
Yeah, absolutely.
So that's what we thought was a good approach for teaching.
George, you want to go ahead? Yes.
Yeah, definitely. Also because we are in the same country, and Mexico. I think it's a bit similar to Latin America. What I find the most interesting thing is, since I came here, it's the lack of regulations and about saying you cannot do anything. Is actually you don't have anyone to stop you. So if you are if you have a good idea and there are a lot of industries actually interested in implementing, even the governments, you can just propose. If you just show that you can, they're really open. I mean, the only thing is your responsibility of making it happen in a proper way. But I'm seeing there is a lot of openness. So what I can say about Latin America is that it's not Germany where you have to follow a specific process and have all the permissions. It can happen from one day to another. You can make a crazy things and installation of public projects. The problem is actually the resources. Maybe as a donor is saying, it's not that every school has a robotic arm or there's not such equipment. But I think in the moment that it will start, it will be a boom. It will be really fast growing.
Yeah. That's true. I think Sara can jump in here because you're sitting right in the middle of so many robotic fabrication labs and industries. So yeah. Yeah, we can't hear you, Sara. I don't know, your mic is.
How about now?
Yeah.
Excellent. Great. Yeah, I wanted to add that for us, it's pretty incredible to see the languages that we're using in terms of scripting and programming, and how immediate the translation is between ideas and materialization. And I'm mentioning this because at Lawrence Tech, at the College of Architecture and Design, we have a required course for all sophomore that introduces them to like a kind of a survey of digital manufacturing techniques, starting with like simply with laser cutting, and then we explore robotic, like simple robotic fabrication using the clay extruder and the hot wire cutter, 3D printers as well. So they have a sense very early in their career, the students, of really how you can, like how Adorn said, like iterate design ideas and kind of like make things not only repeatable, but you can augment intelligence after each step and each iteration. So we really want the students to understand these things. And actually we used the Digital Futures platform and opportunity for teaching an online workshop to test a method to implement those topics also in the master, because in our master is entirely online. So like our target is like students that work, students that have, you know, like their daily schedule, but they and usually we teach at night, and they don't have a digital fabrication course in that instance. So we're really testing things and using those processes as a proof of concept, right? And I'm always amazed when a student sends me a script and I'm there next to the robot, I plug in the USB and the robot executes the instructions. So we are trying like to make, after each iteration, we're trying to make the process better and better, and also like more clear for the students to understand. And I think it was a common topic today, what we learned from reality. So like we have very precise digital information, but then we have materials like sand, we have materials like clay that has like different levels of humidity in different settings, and then the speed of the tools, the settings of the tools play a role in all of these things. So it's like trying to really understand how to get to that granularity of learning experience and trying to express that always through a digital environment, which I think is absolutely fascinating. And if I can, yeah, you can jump in.
No, of course, elaborate. I think, yeah, I just have some more just thoughts on where we are heading with this direction, because I feel that robotic training is not just limited to the classrooms anymore. It is we are equally responsible to educate even in the industry, or create almost like manuals, right? For someone to be able to use any of these tools with a certain kind of understanding. For example, Mohamad's your work at OTF, and OTF has always been this think tank, right? To work with geometries, forms, and also get materially informed. I think this is this is very interesting what's coming out of all the teaching and understanding of robots, even though we are all located in different parts of the world. It's that one kind of machine which we are constantly, all of us are engaging with in our own different ways and our different understanding. I also want you to I just want some thoughts on what are your thoughts on cloud remote controlling of the robots, because now that's coming up as one of a good strength of online teaching, that you can control a robot which is located maybe thousands and thousands of kilometers away from you, and you can still work with that. So have any of you experimented with that front, or worked with cloud remote controlling? I think, Sara, you are the person who's who's connecting between the student, and you are trying to work with their files while they are located in different parts of the world.
Yeah, I'm the translator for them. Like, I'm that cable connection between the students and the robots.
Yeah. Okay, maybe some thoughts we can all share later. But just going back to your work at ETH, and of course the work related to intuitive robotic fabrication. It's a very interesting kind of an understanding of human and robot interaction, right? So, and a similar kind of thing happened even with your work at ETH, Adon, where you were sensing the built environment in the real time, or things that were going in the real time. So what are your reflections on this process, or this understanding of robot working alongside some real time simulations that are happening? Is the process really feasible to do if you do not have the right kind of equipment? Because I know, Adon, you showed some things that you can do actually with a mobile phone by scanning the environments and scanning things which are around you. So where do you see this field heading with machine learning and AI and real-time sensing of material behaviors?
And I would like to queue up a question as well. And how do you see those applications in the architecture field, like jumping off of the research environment?
Yeah, sure.
Yeah, thanks for asking. And I would like to answer the Sarah's question first. I think it's a really good question, because it was really on a small scale, sort of in a demonstration with a machine learning and simulation, right? But however, we are considering this sort of design tool with the sand as a reusable formwork for concrete, for example. So we're just digging the sand with robotic fabrication and computation simulation, and cast the concrete on top of it. And then we again start excavation on the sandbox and obtain a different, for example, the textures with the different patterns, and then we cast the concrete on the same sandbox again. So theoretically, of course, we needed to solidify the sand with oil sort of, or binders, but it will be possible to, let's say, use a reusable formwork with our method. And to the first question, it's really a matter of adaptability, I think. Of course, it's possible to understand such a natural granular materials with an iterative process, like sort of traditional carpenters do by hands, with so many, let's say, training with an actual materials, which also costs time and space, right? So with the machine learning, it will be possible to, for example, adapt with a different granular size, like a clay or other materials, like a concrete, maybe. So without spending, let's say, extra or additional training cost. So which makes sense to use machine learning or hire machine learning for such an unseen situations without an extra cost.
Interesting.
Yeah, I also think that if machine learning is applied through the process, it has a lot of advantages for this kind of on-site fabrication. In this project that I showed, we were not using AI or machine learning. We were just adapting through the scanning. So, and maybe it's different, as Ko said, for processes like building with materials that keep their conditions not what I mean is like not liquid materials or quasi-liquid like spraying or clay. It might be more feasible at this point of the research to use this in on-site fabrication. For us, it was very interesting because it was all an adaptive process. And I personally really like this theme, and I based my thesis on this because I see the potential, and I think that robotic fabrication was kind of left behind for on-site fabrication, like compared to other type of disciplines. So working on that and towards that makes sense for the challenges we have today. And I would just say that there are a lot of differences between the digital world and the physical world at the moment. So I think that trying to fit into those differences and characteristics of the materials through research makes a lot of sense.
Yeah.
And it's a bit of what Mohamad was saying as well.
Yeah.
And back to your point, I think that we are like pushing this knowledge and teaching all of these things because we believe that the future of construction will include robotics, right? And so like, and to a certain extent, of course, like we know how to operate with these tools, and we're trying to explore new methods and new ways of making this kind of pedagogical experience more immediate. But at the same time, and I think that emerged a little bit through the workshop presentations today, we are also like framing the work in a way that we can create narratives and talk about upskilling the workforce and talking about, you know, like imagining scenarios in which we have to deal with complex data or climate change, and we can control precisely some of these processes with digital fabrication, like the control of the energy consumption, the control of the materials. So I just wanted to add the fact that for sure there's a lot of technicality into this, but there's also an opportunity to speculate on like the cultural effects on being like in this environment as well. Yeah, I'll leave it that way. Let's think about this stuff as well.
Yeah. Yes, but any final thoughts you guys are most welcome to add on. We can continue the discussion, but it was a great discussion just to even see where we all are, and of course how the students are interpreting the work and how students are taking it forward and how the workshops have turned out to be. Yes, that brings us pretty much to the end of the session. Any thoughts, any questions, please drop it on the chat, on YouTube. Our audience is always active post the session as well, discussing the work. So thank you so much for joining in. And for next week, we have a first young call of this year on Metaverse. So please join us for some amazing presentations from a bunch of selections that were made on the submissions done on this topic of Metaverse. So more young calls to be followed in the next few months. So stay tuned. Thank you, Sara,
Thank
Reem,
you.
Mohamad, everyone. Go.
Thank you, everyone.
Yeah.
Thank you, everyone.
Thank you all.
Fantastic.
Ta. Have a
Ciao.
wonderful weekend.
Yeah.
Ta.
Yeah.
Ta.